Okay, students, we are dealing with polymers chapter, and we have started with the classification of polymers. Now, we have seen there are many ways of classifying the polymers. First, we started with classification based on source. There we got three, right? Natural, semi-synthetic and synthetic. Then based on structure, we had three more, right? They were linear, branched and network. Then on the mode of polymerization, we had addition polymers and condensation polymers. And we had started with the fourth classification, that is based on molecular forces, right? There we had seen, first one was elastomer, elastomers. Second one was fibers. And we had started in fact with the third one, thermoplastic polymer. Now these are linear or slightly branched long chain molecules, and they will repeatedly soften on heating and then harden on cooling. The reason for that is they will have molecular forces which are in between that of the elastomer. This one has a very weak force and this one has a very strong force. So intermediate force, neither very weak, neither very strong, that exists in thermoplastic. Therefore, on heating they will soften and on cooling they will harden. So you must have seen best examples are PVs, polymerized. Okay. Are very good examples of thermoplastic polymers which soften on heating and then harden on cooling. And the last one, as far as this classification goes, is thermosetting polymer. Thermosetting polymers are, they contain highly cross-linked and branched, you can say. So when you heat them, what happens? They turn into very extensive cross-linking going on, and they will become an infusible mass, of course. That means once you use them or once you heat them, you can't reuse them again. So they turn into an infusible mass due to that extensive cross-linking and branching that takes place. So bakelite is a very good example here. What is bakelite, right? And even you have urea formaldehyde resins. These are all thermosetting polymers. So, depending upon what molecular force exists between the monomers, you have four types of polymers. Elastomers, which have stretchable quality. These are very strong ones, fibers. These are natural rubber can use. Here you can say nylon 66. Then thermoplastic, which soften on heating, harden on cooling. And these are highly branched, highly cross-linked. So as soon as you heat them, they will turn into an infusible mass. So this is how we classify the polymers. So four different classifications are given to you. First one based on source, second one based on structure, third based on mode of polymerization, and the fourth one based on molecular forces. Now we will go into the types of polymerizations, and first one is the addition polymerization. So in addition polymerization, which is also called as here in this, you will have to study certain molecules, okay, which will undergo addition polymerization, especially if you want to do addition polymerization, the best raw material is always an alkene. Alkenes readily undergo addition polymerization. Okay. Other than that, you can also use dienes. Okay, like butadiene, you can use butadiene. So alkenes and dienes, and also their derivatives are very good, raw material for doing your addition polymerization. So you can get one of the best addition polymer is polythene. So where you have low density as well as high density polythene, you have polytetrafluoroethylene, then you have polyacronym. All these are addition polymers. Okay. And as I told you, alkenes, dienes and their derivatives can easily made to undergo addition polymerization using a catalyst which is called as the free radical initiator, because the mechanism that these undergo is always the free radical mechanism. So these alkenes, dienes as well as their derivatives will follow the free radical mechanism and will undergo addition polymerization to give you addition polymers. Okay. But they always need a catalyst. That catalyst is called the free radical generating initiator. So, alkenes, dienes and their derivatives, okay, in presence of free radical generating initiator, which is the catalyst, can undergo addition polymerization. Now, this free radical radical generating initiator can be a peroxide like benzoyl peroxide, or you can use acetyl peroxide. We can also use tertiary butyl peroxide. So all these are the catalysts, the free radical generating initiators. So when you take any one of these alkenes, dienes or their derivatives in presence of these catalysts, they will undergo free radical mechanism and you will get addition polymerization. Now let's try and get an idea about how that free radical mechanism takes place and you get an addition polymer. So let's start with an example. Let's say if you want to know how polyethylene might be prepared by addition polymerization. So a free radical mechanism always involves 3 steps. First one is initiation. This is the first step in free radical mechanism. Last step also we had this, right? Free radical mechanism in the halogenation reaction of alkanes. Now here, let us say we start with ethene and using that free radical initiator, generating initiator, the catalyst. Let us use benzyl peroxide. Okay. So the first step is this initiation. What happens is this C6H5 dash C double bond O dash O dash O dash C double bond O dash C 6H5. Okay. Now this is benzoyl peroxide. Now it will undergo division. phenyl free radical. So here we will get 2 C6H5 dash C double bond O dash O minus. So this bond will break here and we will get 2 phenyl free radical. Okay, so this is your phenyl free radical. So the benzyl peroxide first undergoes fission and generates 2 phenyl radicals. So this is how it initiates. As soon as this is formed, it will attack an ethene molecule. So C6H5 dot. Suppose if it comes near an ethene molecule, right? So that will convert into a free radical of this form. This is initiation. This is the first step in this process. So as soon as this radical is formed, it attacks more ethene molecules. So C6H5 and CH2 dash CH2, this radical will attack more. This is now the second step, and the second step is called propagation. So in the first step, this is how it initiates. The benzyl peroxide will undergo fission to form 2 phenyl free radicals. That phenyl free radical will attack an ethene molecule and you get this free radical. Now it propagates, the chain propagates. Now this radical attacks one more ethene molecule. What do you get? You get C6H5 dash CH2 dash CH2 dash CH2 dash CH2. See? The length of the chain has increased or the reaction is propagating. Suppose if it gets n number of molecules, or if this goes on joining with n number of ethene molecules, what you will get? Let us say you will end up with something like this. I'll write it here. C6H5 dash CH2 dash CH2 dash CH2 dash CH2. So this length of the chain will increase. It goes on increasing like this. Okay, so this is how it goes on propagating. And the last step in free radical mechanism is termination. So two such chains might come, and there are various possible ways in which the reaction can terminate. So let us say we have two such chains with us. So C6H5 dash CH2 dash CH2 n number of times, that's CH2 dash CH2, and we have another chain CH2 dash CH2 n number of times, so CH2 dash CH2. Okay, so now the reaction have to stop somewhere. So there are various possible ways. One possible way I can write is this can combine, these two chains can combine, and you can get C6H5 dash CH2 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 dash C6H5. This is n number of times. N number of times. Okay. So this is how polythene is formed by addition polymerization. So this is the free radical mechanism. involves three steps: initiation, propagation, termination. So first, the free radical generating initiator, the catalyst, benzyl peroxide, will undergo fission to create two phenyl free radicals. Now this phenyl radical will then attack an ethene molecule and the attachment takes place. Then the chain goes on propagating when this radical, that is, it goes on increasing or adding more and more ethene molecules, and the chain goes on propagating. Okay. Now it can terminate in many ways. I have given one way of the termination of the reaction. Okay. So this is how addition polymerization takes place. So let's try and now see some addition polymers. Okay, the most common that we use almost everywhere now, it has been, it has become a complete hazard to us. So because of the pollution it is creating all around, that is polythene. Now there are two types of polythenes. One is called the LDP. It is low density polythene. Now the starting material and the reaction we already have written yesterday is simple. You need ethene n number of times, and this is in presence of a catalyst. There is the free initiating, the free radical initiator or the generating initiator. But the pressure that is required, or you can say ethene is subjected to very high pressure, somewhere around 1000 to 2000 atmospheres, and at very high temperature. It has to be subjected to very high temperature, somewhere around, you can say 150 Kelvin to 570 Kelvin, this range, under the presence of initiating, that is the catalyst. This will give you this monomer. Okay, and then it goes on adding. This is your polythene. So when ethene is subjected to very high pressure, around 1000 to 2000 atmospheres, at a very high temperature, 350 to 570 Kelvin, then using a catalyst, you can use a peroxide as a catalyst. What do you look at? It is converted into low density polythene. Now low density polythene is very hard but flexible. It is tough. It is flexible. It is non-conductor of electricity. So therefore, it finds immense use in electrical insulations. Wires are insulated. Electrical wires are insulated using this. You find a number of uses of LDP. Okay. Similarly, we have HDP, high density polythenes. Now here, to prepare, the raw material is the same. It is the same ethene we are going to use, but the pressure and the temperature required will be less, because here we use a catalyst called Ziegler-Natta catalyst. So this catalyst is used in the preparation of HDP, high density polythene. Now what is the Ziegler-Natta catalyst? It is triethyl aluminum plus titanium tetrafluoride. This is called the Ziegler-Natta catalyst. Triethyl aluminum titanium tetrachloride. Okay. Now the same reaction, only thing is that here, because of the use of this catalyst, the temperature and pressure around 6 to 7 atmospheres, okay, then temperature around 333 Kelvin to 343 Kelvin is used, and Ziegler Natta catalyst is used. C2H5 thrice Al plus we use PiCl4. So that also gives you. Okay, so this HDP is also very tough. It is a non-conductor of electricity, bad conductor of electricity. It has high strength. So therefore used to prepare buckets and all those plastic things that we get, plastic buckets, tumblers, all these things are prepared using HDP. So this is how we prepare polythene, whether LDP or HDP, using ethene and making it to undergo addition, polymerization using a catalyst like a peroxide catalyst. Similarly, we have another addition polymer, and that is tetrafluoroethylene. Okay, this is also called as Teflon. No, I've seen Teflon, where most of you must have seen the non-stick cookware at home. So there's a Teflon coat there on the utensils that is used, right? Now this is also an addition polymer. So we have to take tetrafluoroethylene, so n number of times. So same temperature, you have to subject it to high pressure and temperature under a peroxide catalyst. In presence of peroxide catalyst. So pressure as well as temperature. So this also will undergo addition polymerization, and you will get this particular monomer. This monomer you will get. Okay. So this n number of times is Teflon or polytetrafluoroethylene. Okay, mostly used to prepare seals of engines, even gaskets. Then as a non-stick coat. So these are the various uses of polytetrafluoroethylene. Right? Similarly, we have one more, that is polyacrylonitrile. Polyacrylonitrile. So CH2, double bond CH dash CN, n number of times. Okay, this is poly. Not poly, this is acrylonitrile. same, you under the influence of a peroxide catalyst. Okay, this also will undergo addition polymerization to give you a monomer like this. This is the monomer you will get, and when it joins, adds on like this, you get this polyacrylonitrile. Especially used to prepare synthetic fibers. Orlon is one. These are all synthetic fibers where we use acrylonitrile. Okay, so you have seen now addition polymerization. Now this addition polymerization takes place by free radical mechanism. And generally what compounds are used? Generally alkenes, dienes and their derivatives. So this becomes the raw material. Now these will undergo this mechanism under the influence of a catalyst or in the presence of a catalyst, and that catalyst is also named as free radical generating initiator. And this most of the time is a peroxide. So peroxides can be used. So normally we use either benzoyl peroxide or acetyl peroxide or tertiary butyl peroxide. So the mechanism follows 3 steps: initiation, propagation, termination. Okay. Then we learned certain important addition polymers. So first one was polythene. Right? So in polythene, 2 types: LDP, HDP, high density polythene, low density polythene. Then I told you about Teflon, which is nothing but tetrafluoroethylene. Right. Then I told you about polyacrylonitrile. These are all very important addition polymers. Same way you have to study condensation polymers. Okay, and some condensation polymers. So in condensation polymerization, what happens? We join 2 monomers to form a polymer with the liberation of a water molecule or even an OH or even an HCl. So you can combine 2 things. Okay. Now when you come to condensation polymerization, there are many sections in this. You have polyamides, you have polyesters, then various examples in polyamides, then in polyesters, etc. So I think it is better for us to take it in the next class. Okay.